Welcome to Nucleus Communications tutorial. If you have not yet watched the Nucleus overview video, please start there first. This video will guide you through the process of defining communications to all of the remote devices required for your control system. This video assumes you have opened a new project and you are creating the communications links as the first required step in the development of your control system. Select the Communications Builder section.
The configuration on this screen shows 4 server groups, CSO1 through CSO4. A server group is a collection of device links for each individual server. When using a standalone HMI, only CSO1 can be used. For network systems from 1 to 4 individual communication server applications can be used, or 2 redundant pairs. For more information on this topic, watch the video tutorial on server redundancy.
Now, select the CSO1 server and click the button Edit Selected Comms Links. Click on the CSO1 server at the top and change the server IP address to the IP of the computer you are using. In our case, it is 192.168.1.115. Now, with the server at the top selected, click on the new button.
This screen shows a list of available protocols. A protocol is a set of rules governing a communications stream between your Nucleus control system and a PLC, OPC server, MQTT broker, IoT device, or some other remote processor. Many SCADA systems use OPC servers exclusively as an in-between translation service. While this reduces the work in assigning I/O from the HMI perspective, this method is slow and quite expensive in comparison to the built-in protocols shown here, such as Modbus TCP or the native PLC protocols for AllenBradley, Siemens, and GE Emerson. Most native protocols are register-based, and this makes them very fast. Examples are AllenBradley Legacy, GE Emerson, Siemens S7, Modbus, and the train control protocols Data Train 8, Genesis, and the LCP protocol. On the other hand, AllenBradley Logics and OPC protocols allow the Nucleus developer to connect to a PLC or OPC server and browse internal I/O they wish to communicate with. This makes I/O assignment much easier, but this communication method is less responsive. However, in some cases, this is the only option if the PLC logic streams are already set and the client will not allow you to restructure communication variables into arrays. All other protocols require a starting register selection and a quantity of registers to add to the stream. When this is done within this communication builder, your I/O to that device is created automatically. But your I/O must be manually named as described in the I/O videos following this one. In addition, the MQTT protocols require I/O to be mapped using topic names. This will be described in the Help Center documentation. Now, we will select the AllenBradley Logics protocol and then select the Save button to close the dialog.
Now, click on the source value in the tree and change this value to AB1. And we will also set the route path to the IP address of this AllenBradley PLC on our network. Please note the description of the route path property at the bottom of the window.
We will leave our controls to the PLC as momentary controls. This means the controls in this link will only be set at a high control value for 3 seconds and then drop back to 0. So in this case, any necessary latching must be performed within the PLC ladder logic. If you select latching, the control values will stick until changed within your control system. This property initially sets every control to momentary or latching for the link, but in the project data section you can set individual controls to either momentary or latching if you wish. We will explore this later. For the AllenBradley Logics processor, there are 2 modes for defining I/O to the PLC. One method is to use structured arrays so that the communications is similar to register-based protocols like Modbus and GE Emerson. Arrays are by far the fastest communication method. Another upside is that this form of communication will create all the I/O for you automatically. The downside is that you have to name each point to know what digital, analog, or real floating point variable you will be using when assigning to graphics, alarms, and other features of the control system. The second and usually more popular method of the I/O assignment is to activate PLC Browse. This feature is only available on AllenBradley Project Logic PLCs and OPC servers. You must be connected to the PLC to use this feature of the I/O selection. When connected, you can select individual I/O from inside the PLC to define within your control system. You only need to be connected to the PLC during this I/O creation phase. After that, you can continue to define screens and options while offline with the PLC. The default state of a new AllenBradley Logics link is to use I/O as registers, or as we call it, structured arrays. This method will be our first link. To do this, we typically define an integer array in the PLC that we will use to receive indications, and a second integer array we use to send controls. Then we break those down to Boolean registers where needed. This is by far the fastest method to send and receive data. The amount of data we stream to this device depends on the number of words defined. The data size depends on the type of array. The options are integer 16, integer 32, and single for floating point values. You can only assign one indication array read and one control array write per link. So if you need both of the integers and reals, 2 links to the same PLC are needed. Otherwise, we use the PLC Browse feature where you can select multiple arrays in the same link. Once everything has been configured for this link, press the Save button. This action will create all of the I/O defined for your link if you use the structured arrays. If you use PLC Browse, you will define your I/O manually in the project data section in the next videos.
Now, we will set the data size, the number of words to read and write, and set the array name defined internally within our PLC. Note that all Nucleus communications protocols connect directly to the remote devices. And the use of registers and arrays reduces the tag count dramatically and radically improves communication speed. Once everything has been configured for this link, press the Save button. This action will create all of the I/O defined for your link. We will go back to the project data section to see the new I/O created to communicate with this PLC device with the source name of AB1.
Now, let's return to the Communications Builder and add a second AllenBradley link where we can select I/O directly from the PLC. Watch closely as we add a new link and name the source as AB2. This link will go to the same PLC. It won't use the read and write sections. Instead, we will activate PLC Browse so the I/O is defined manually via the indication and control windows in the project data section. We will show this process in the next 2 tutorial videos. For the moment, let's delete the second AB2 link because we don't want to define that browsed I/O in this video. We will expand on this in the following 2 videos. For now, we just want to show how communications works with the automatic creation of I/O.
Now, to speed things up, we will import 2 more Modbus links that were exported in previous projects and add those to our new control system. We will need to set the source names to save the new links. The second imported link will use latched controls, where the register sizes are single for floating point values. For the floating point link, the indication and control registers are set to the same Modbus addresses for a read-write type interface to and from the same registers. Now we will save our changes, and the I/O for these two new links will be created for us. The following illustration shows how you can define an array within a Logics processor that uses a mixture of digital and analog values. We will show you how to break up your I/O to fit this array map later in this presentation. Before we test these new communication links, let's adjust the format of the I/O we will be sending to AllenBradley PLC, as we saw in the illustration. The default setup when defining the communications to a PLC or Modbus device is to build analogs as either integer 16 or integer 32 or single to represent floating point. But we want our array to contain a mixture of digital and analog values as integer 16. So let's change this in the project data section for the source AB1. The purple backgrounds in the I/O lists allow us to change the default analog structure to contain digital values as well. We will do this for the first two words in the AB1 link. Changes are saved automatically with this action. We can show these new communication links in the communications tester, but since this is a standalone project where the communications is built into the HMI station, we will show this communication inside the HMI station. Note that while we wait for the HMI station to start, we can see the project name and the revision number we entered into the project options window. Use this revision number to represent your distribution revision in the client's facility. And once the application is running, we see on the title bar indicating that this is a standalone instance of the HMI station. We'll click on the status button and then communications to see our values change when we communicate to our remote devices. This feature of the HMI station is only available on standalone systems. On network systems, the communication server applications will run on a server computer and not inside the HMI stations. Now select the I/O tabular to see all the changing values from the PLC. This concludes the communications portion of the Nucleus system. Be sure to view the Help Center for more information. Our next video will show you how to use the export and import features to import names and descriptions in Excel to import into your I/O list for indications and controls. This will provide more meaningful descriptions when using your indications for graphics assignment or monitoring via the communications or I/O tabular interfaces.